There is a single concept in physics that controls the flow of time, the fate of stars, the weather on Earth, and even the existence of life itself. It's one of the most important ideas in science, and yet, many people misunderstand it. I'm talking about entropy. Entropy is often described in textbooks as disorder, or the tendency for things to move from order to chaos. It governs why a hot cup of coffee cools down instead of warming up again, why you can scramble an egg but never unscramble it, and why the universe as a whole is gradually winding down towards a mysterious heat death. It might even be the reason we experience time moving forward and not backward. Imagine if time ran in reverse. You might see spilled water gathering itself back into a glass, or shattered pieces of a vase flying up and reassembling perfectly, or smoke undiffusing from the air into a candle. In reality, none of those things ever happen. Once a vase shatters, it stays shattered. Once smoke has dispersed, it won't spontaneously collect back. There's a physical reason for this irreversibility, and it's directly tied to our mysterious concept. Sounds dramatic? It is. Entropy has been called the arrow of time because it gives time a direction. It's the ultimate referee in nature, telling us which processes can happen and which cannot. Yet despite its fundamental importance, entropy is notoriously misunderstood. Many explanations simply call it disorder or randomness, which is true in a sense but doesn't capture the full picture. In everyday life, people rarely think about entropy at all, even though it's at work in every moment, from the molecules in our bodies to the formation of galaxies. So what is entropy, really? Why does it always seem to increase, and why can't we ever decrease it, at least not without paying a price? To answer that, let's start with a simple question. What does Earth get from the sun? You might say energy, sunlight and warmth. Indeed, every day Earth bathes in a huge amount of energy from the sun's rays. But here's a twist. Earth also radiates essentially the same amount of energy back into space as heat. If it didn't, our planet would keep heating up relentlessly. So if the energy coming in is balanced by energy going out, what are we truly getting from the sun? It's not just about the amount of energy, it's about the quality of energy. The sun provides Earth with low entropy, highly concentrated energy in the form of intense visible light. Earth then re-emits that energy as high entropy infrared radiation, which is diffuse and much lower in temperature. In other words, the sun sends us useful, ordered energy, and we return it to space in a much more spread out, useless form, waste heat. This difference is the key. By converting the sun's concentrated energy into dispersed heat, the Earth and everything on it, including life, can perform work and thrive. Entropy, in essence, is a measure of how spread out and unavailable for work energy becomes as it is transformed. To truly understand this concept and why entropy tends to increase, we need to go back in time to the early 19th century, when scientists first grappled with the puzzling limitations of energy use. Our journey begins with steam engines and a young French engineer named Sadi Carnot. Our story begins in the winter of 1813, in the midst of the Napoleonic Wars. France was under siege by Allied armies, and a 17-year-old military student named Sadi Carnot, the son of one of Napoleon's generals, found himself swept up in the chaos. Young Carnot was eager to serve his country. In early 1814, he joined the defense of Paris against the invading forces. Paris fell after only a day of fighting, leaving Carnot disillusioned. In the aftermath of the war, France's glory had faded, but Carnot's mind turned to a different kind of battle, the race to improve technology, especially the steam engine. Steam engines had been around for over a century by Carnot's time. from the primitive Newcomen engine of 1712 to James Watt's improved engines in the late 1700s, and they powered the Industrial Revolution. However, they guzzled fuel for relatively little output. Most of the heat energy from burning coal was wasted. Improving efficiency wasn't just an academic exercise, it was the key to advancing industry and transportation. If France could build engines that produced more power from the same amount of coal, it would gain a huge advantage. Carnot became obsessed with understanding what fundamentally limited engine efficiency. Steam engines were the high-tech marvels of the day, powering ships, factories, and mines. They promised industrial and military might to whichever nation mastered them. But there was a problem. Even the best steam engines were terribly inefficient. At that time, a good engine might convert only around 3% of its heat energy into useful work. The rest of the energy just dissipated, wasted as excess heat. British engineers seemed to be ahead in squeezing more work from their engines, while French designs lagged. Carnot wanted to know why. What was limiting the efficiency of these machines? Could one perhaps design a perfect engine that harnesses all the heat without any waste? Carnot dove into this problem. For years, he studied how engines operate and imagined an idealized heat engine with no friction and no losses. A perfect engine that would set the absolute standard for efficiency. In 1824, he published his findings in a modest book that later became a cornerstone of thermodynamics. In this work, Carnot described a theoretical engine cycle, now known as the Carnot cycle. It worked like this. The engine takes heat in from a high-temperature source, uses that heat to expand a gas and do work, pushing a piston, for example, then dumps leftover heat into a low-temperature sink, and finally the gas is compressed back to its initial state to start the cycle again. Importantly, Carnot imagined this ideal engine to be reversible, meaning it could run forward or backward without any loss of energy. If run in reverse, it would act like a refrigerator or heat pump, absorbing heat from the cold side and releasing it to the hot side while consuming work. Carnot's analysis revealed something profound. Even this perfect, reversible engine could not convert all the input heat into work. There was an inherent limit to its efficiency, determined solely by the temperatures of the hot and cold reservoirs. In simple terms, the greater the temperature difference between your heat source and your heat sink, the higher the possible efficiency. But to reach 100% efficiency, you would need the cold end to be at absolute zero. In any real scenario, with a finite cold temperature, some heat must remain and be expelled to the cold reservoir. In other words, no heat engine can ever be 100% efficient because you always have to dump some waste heat. Carnot realized that to complete the cycle and return the working gas to its starting condition, a portion of the energy must be released to the cold side. Not all the heat taken from the hot source can be turned into mechanical work. This was a startling insight. It meant that there is a fundamental barrier preventing the complete conversion of heat into useful work. A barrier no clever engineering can overcome, only mitigate. Carnot's work implied that some fraction of energy will always end up spread out as waste heat rather than staying in a concentrated form as work. His book initially didn't attract much attention outside a small circle, but in the coming decades, scientists realized its importance. One of them was a Scottish physicist named William Thomson, later known as Lord Kelvin. Building on Carnot's ideas, Kelvin formalized the concept of an absolute temperature scale, the Kelvin scale, with zero at the point where an engine would theoretically achieve perfect efficiency. This helped cement the idea that absolute zero is a special, unattainable limit of coldness where molecular motion nearly stops and no heat can be extracted. In fact, it's impossible in practice to cool any system all the way to absolute zero. The closer you try to get, the harder it becomes to remove the last bits of heat. This is known as the third law of thermodynamics. As temperature approaches absolute zero, entropy approaches a minimum value, but you can never quite reach that perfectly ordered state of zero entropy. Meanwhile, a German physicist named Rudolf Clausius was also exploring the implications of Carnot's work. In the 1850s, Clausius formulated a clear general statement: heat cannot spontaneously flow from a colder body to a hotter body without external work being done. This became one of the statements of the second law of thermodynamics. Clausius also sought to quantify the loss that Carnot had identified, the portion of energy in any process that becomes unavailable to do work. He introduced a new quantity to measure how much energy is dissipated or spread out in a thermodynamic process. In 1865, he gave this quantity a name: entropy. Clausius chose the word entropy from Greek roots, entropia, meaning a transformation or turning. He intentionally coined it to sound similar to energy, highlighting their relationship. With this concept, he formulated the laws of thermodynamics in a famous statement: the energy of the universe is constant. The entropy of the universe tends to a maximum. In other words, energy cannot be created or destroyed, only converted from one form to another. But every time energy is converted or transferred, the total entropy, the measure of energy dispersal or disorder, increases. In plainer language, you can't get rid of entropy. At best, you can shuffle energy around, but overall, the amount of usable energy decreases as entropy rises. This was a milestone in science. For the first time, a fundamental law of physics introduced an arrow of time. Most basic physical laws, Newton's laws of motion, Maxwell's equations of electromagnetism, etc., are time-symmetric. They work equally well forward or backward in time. But the second law of thermodynamics says there's a preferred direction, from lower entropy to higher entropy. Nature moves toward states where energy is more spread out. A hot object in a cool room will cool down and warm the room, not the other way around, because that results in energy becoming more evenly distributed between object and room, higher entropy. You'll never see the reverse, the room's heat suddenly concentrating into the object to make it hotter, because that would mean a decrease in total entropy, which is astronomically improbable and would violate the second law for an isolated system. So, by the mid-19th century, the concept of entropy as the measure of energy dispersal and lost useful energy was established. Still, one might ask, why does entropy have to increase? What's really going on deep down in the micro world to cause this one-way street for natural processes? To answer that, we turn to the work of an Austrian physicist named Ludwig Boltzmann, who looked at entropy from the perspective of atoms and probability. Ludwig Boltzmann entered the scene in the late 19th century to tackle the question of why entropy inevitably increases. Boltzmann was a firm believer in the atomic theory of matter, the idea that all substances are made of immense numbers of tiny particles, atoms or molecules, moving about. At the time, not everyone accepted that atoms were real, but Boltzmann's work assumed they exist and used them to explain thermodynamics. He argued that entropy is fundamentally a matter of statistics and probability. In Boltzmann's view, entropy measures the number of microscopic configurations, the detailed arrangements of all those particles or energy quanta that correspond to a system's overall state. Consider a simple example. Imagine you have two equal-sized boxes connected by a door, and inside there are 100 gas molecules bouncing around. What are the chances that all 100 molecules end up in the left box at some moment, leaving the right box empty? It's not zero, but it's extremely small. There are far more ways for the molecules to distribute themselves roughly half and half between the two boxes, some in the left, some in the right, than for all to crowd into one side. If the molecules move randomly, overwhelmingly, they will be found in a fairly even spread, simply because that corresponds to vastly many possible arrangements. The state with all molecules in one box is highly ordered, very low entropy, but also highly improbable. Essentially, only one microarrangement yields that outcome. In contrast, the state with about 50 molecules in each box is disordered, higher entropy, but enormously more likely because there are countless combinations of molecules that achieve that balance. Boltzmann quantified this idea with a famous relationship. Entropy is proportional to the logarithm of the number of microstates available to a system. In plainer terms, if a system can be arranged internally in an enormous number of different ways that all look the same from the outside, then it has high entropy. If there are only a few internal arrangements possible, it has low entropy. More possible microstates equals higher entropy. This statistical viewpoint explains why entropy tends to increase. Any system will naturally evolve toward the condition that can be realized in the largest number of ways, simply because there's more chance for it to happen. It's not that an egg wants to scramble, or that a deck of cards wants to be unordered. It's that there is only one way for an egg's molecules to be neatly contained in a pristine, unbroken egg, and zillions of ways for them to be a spilled, scrambled mess. If you jostle the system, shake the egg, or shuffle a sorted deck of cards, you're almost guaranteed to land in one of the numerous disordered states, not the unique ordered one. Think of a Rubik's Cube. There is exactly one configuration that is perfectly solved, completely ordered, and roughly 43 quintillion possible configurations in total. If you were to twist a solved Rubik's Cube randomly, the chance of accidentally returning it to the solved state is virtually zero. Most moves will lead to one of the astronomically many scrambled states. Likewise, randomness drives systems toward disorder, simply because disordered arrangements are overwhelmingly more common than perfectly ordered ones. Once an egg is broken, the molecules quickly disperse into one of the countless jumbled configurations, high entropy, and the odds of all of them randomly moving back into the one configuration that makes a pristine egg, low entropy, are effectively zero. Thus, the second law of thermodynamics emerges as a law of probability. Going from order to disorder is easy because disorder is statistically favored, whereas going from disorder to perfect order is so unlikely that it will never be observed for a macroscopic collection of particles. This also gives a deeper interpretation of the arrow of time. We can now say that the forward direction of time, what we call the future, is the direction towards more possible microstates, i.e., higher entropy. Sir Arthur Eddington famously said, "Time's arrow is a property of entropy alone." The idea is that if you reverse time, you would see entropy going down, which is so improbable that it essentially never happens for a large system. That's why we remember the past and not the future. Our memories and records were formed when entropy was lower, and as entropy increases, those records remain as evidence of the past. But there are no records of a future that hasn't happened yet, and there could not be, because that would imply somehow decreasing entropy to create a memory of something before it occurs. It's natural to wonder, is there any clever way to beat the second law? Could we somehow separate fast, hot molecules from slow, cold ones and generate useful energy without increasing entropy elsewhere? In 1867, physicist James Clerk Maxwell proposed a famous thought experiment. He imagined a tiny intelligent being, later dubbed Maxwell's demon, controlling a little door between two chambers of gas. The demon could, in theory, let only fast-moving hot molecules go into one chamber and only slow cold molecules into the other, without expending energy, thus making one side hotter and the other colder. If it worked, this would decrease entropy and seemingly violate the second law. For decades, it remained a paradox, but eventually, scientists realized that the demon itself cannot be ignored as part of the system. To decide when to open the door, the demon must measure the molecules, essentially gathering information about their speeds and positions, and then remember that information. The act of collecting and processing information has an energetic cost. The demon's memory or notepad, for instance, fills up and must be cleared eventually to continue operating, and erasing that information inevitably produces heat and increases entropy. When you account for the demon's efforts, the total entropy still increases. In short, even a demon can't cheat thermodynamics. This resolution revealed a profound link between entropy and information. In fact, in 1948, the mathematician Claude Shannon borrowed the term entropy for his theory of information, defining it as a measure of uncertainty or missing information in a message. The more unpredictable a message is, the higher its entropy. Much like the more random the motion of molecules, the higher the physical entropy. This isn't just a coincidence of wording. It hints that the physical world's tendency to disorder and the abstract idea of information are two sides of the same coin. Acquiring, storing, or erasing information has a thermodynamic price. For example, in 1961, physicist Rolf Landauer calculated that erasing one bit of information dissipates a tiny minimum amount of heat, known as Landauer's limit. In the case of Maxwell's demon, the demon pays that price. Its memory clearing dumps entropy into the environment, saving the second law. In the end, the second law stands undefeated. Even information obeys it. Now, an important caveat. The second law of thermodynamics, entropy tends to increase, applies strictly to closed systems, meaning systems with no exchange of energy or matter with their surroundings. Many systems we encounter are open. They can gain or lose energy, and even matter, from the outside. In an open system, it's possible for entropy to decrease in one part of the system, so long as it increases by at least as much in another part that compensates. In everyday terms, you can locally reverse entropy if you pay the price elsewhere. A simple example is a refrigerator or air conditioner. These devices pump heat from a cold space to a hot space, which by itself would decrease entropy, making the cold inside colder and the hot outside hotter, a more ordered situation. But to do this, they consume electrical energy, which ultimately ends up as extra heat released into the environment. The net effect, when you include the work done by the appliance and the power plant generating the electricity, is an overall increase in entropy. You've moved entropy out of your fridge into the wider world, but you haven't destroyed it. The same goes for something as mundane as cleaning your room. You can decrease the entropy of a messy bedroom by putting everything in order, but the effort you expend burns calories in your body, releasing heat, sweat, and mixing up molecules in the air you breathe out. If you consider yourself and the room together and the food you ate for energy, the total entropy has increased. Your room looks tidy, low entropy, but in the process, the entropy of the wider environment went up a bit. The Earth as a whole is also an open system. We continuously receive low entropy energy from the sun and radiate high entropy energy into space. That flow is what sustains all kinds of organized, low entropy structures on Earth, from weather systems to living organisms. Take a tree, for example. It absorbs sunlight, which is energy in a very concentrated, high-quality form, and uses that energy to build sugars, wood, leaves, highly ordered structures, essentially decreasing entropy locally in the tree's biomass. But in doing so, the tree releases oxygen and, eventually, when its organic matter decays or burns, all that stored energy returns to the environment as heat and randomly distributed molecules. Even in the short term, the tree warms its surroundings slightly during metabolism and transpiration. Overall, the entropy of the Earth plus atmosphere plus surroundings increases thanks to the sun's input, even though the tree temporarily maintains a high degree of internal order. All life works this way. Humans, animals, plants. We create local pockets of low entropy, like our bodies, which are highly organized structures, but only by consuming energy, food, or sunlight, and dumping waste heat and byproducts, thereby increasing entropy in our environment. In fact, some scientists have suggested that life's very existence is tied to the second law's imperative. If the universe tends toward higher entropy, then perhaps systems that accelerate entropy production will naturally flourish. Life could be seen as one of nature's most effective entropy-generating mechanisms. A striking example comes from ocean biology. Sunlight falling on the ocean can be absorbed by the water, but if that water contains photosynthetic microbes, like cyanobacteria and algae, those organisms capture the sunlight's energy, use it to grow and multiply, and then ultimately release it as low-grade heat when they, or things that eat them, metabolize and later die and decompose. Studies have measured that a sunlit patch of ocean water produces substantially more entropy when teeming with microscopic life than it would if it were sterile. In one analysis, the presence of such life boosted entropy production by anywhere from 30% up to several 100%, meaning life was turning the sun's energy into dispersed heat much more efficiently than non-living processes alone. Not only living organisms, but even non-living systems can spontaneously form organized patterns when energy is flowing through them. A classic example is a fluid heated from below, beyond a certain threshold. Instead of just conducting heat in a featureless way, the fluid forms rolling convection cells, circulating loops of fluid that efficiently carry heat upward in an ordered honeycomb-like pattern. Another example is a chemical mixture that, when driven far from equilibrium by a constant energy supply, undergoes rhythmic color-changing oscillations, the Belousov-Zhabotinsky reaction. These are sometimes called dissipative structures, temporary pockets of order sustained by a continuous dissipation of energy. They show that increasing entropy overall doesn't preclude the emergence of local structures. On the contrary, the flow of energy toward higher entropy can create and support order along the way. Life is perhaps the most sophisticated dissipative structure of all. Over time, evolution has produced organisms that are extremely good at taking concentrated energy, sunlight, nutrients, and breaking it down, using it to build intricate structures and do work, all while increasing entropy in their surroundings. A physicist named Jeremy England has proposed a provocative hypothesis that ties these ideas together. He suggests that under the right conditions, matter will spontaneously self-organize in ways that dissipate energy more effectively. Essentially, that the rise of complex structures, possibly including life, is driven by the urge to increase entropy. In plain language, if you shine a steady source of energy on a bunch of atoms for long enough, they might reconfigure themselves into progressively more organized systems that are really good at soaking up that energy and turning it into waste heat. According to this idea, what we call life is just a particularly spectacular example of this kind of self-organization. As England quipped, you start with a random clump of atoms, and if you shine light on it for long enough, it should not be so surprising that you get a plant. In other words, given a sun-like energy source and enough time, the emergence of organized, energy-eating, entropy-producing structures, living organisms, might be expected, rather than purely a stroke of luck. This view is still being debated and tested, but it's fascinating because it reframes life as a natural consequence of thermodynamics. Whether or not life had to arise, one thing is certain. Life doesn't violate the second law of thermodynamics. It obeys it and even exemplifies it. We living beings are open systems that constantly take in low entropy energy, food, sunlight, and expel higher entropy waste, heat, CO2, etc. In the grand accounting, we are continuously increasing the entropy of the universe, just like any other physical process. We're just doing it in a very organized and interesting way internally. And that brings us to the biggest canvas of all, the entire universe. If entropy must increase overall, what does that say about the history and future of the cosmos? On the scale of the whole universe, entropy provides a narrative for both cosmic history and cosmic destiny. We know that if entropy has been increasing with time, the universe must have started in a very unusual state of extremely low entropy. Right after the Big Bang, the universe was incredibly hot, dense, and almost completely uniform. This might sound like a chaotic mess, but in terms of entropy, it was actually an extraordinarily ordered state. The key is gravity. In a simple non-gravitational scenario, like gas in a box, a uniform spread of matter is high entropy because it's completely mixed and homogeneous. But when gravity is in play, a uniform spread of matter is a highly ordered state, with huge potential to become more disordered. Imagine a diffuse cloud of gas under gravity. If it's spread evenly, it's actually a low entropy situation because there's so much potential for that gas to clump together under gravity. Once it clumps into, say, stars and galaxies, you've converted a lot of gravitational potential energy into heat and radiation, thereby increasing entropy enormously. The early universe, being smooth and uniform, was like a pristine low-entropy canvas with enormous room for entropy to grow. As the universe expanded and cooled over billions of years, tiny primordial irregularities in density grew under gravity's pull. Matter clumped into filaments and then into galaxies, stars, and planets. In the process, tremendous amounts of energy were released. When gas falls together to form a star, gravitational energy turns into intense heat. The star then shines, radiating energy away as light and infrared, spreading energy out and raising entropy. When a massive star exhausts its fuel and explodes as a supernova, it scatters its constituent elements into space and often leaves behind a very disordered remnant, like a neutron star or black hole, further increasing entropy. Every process of structure formation, galaxies merging, stars burning and then dying, planets coalescing, has driven the universe's entropy upward. Physicists have attempted to put numbers to the universe's entropy at various stages. As the universe evolved and structures formed, that number skyrocketed. Today, the cosmic microwave background, the faint afterglow of the Big Bang, and all the infrared light from stars and dust contribute a colossal amount of entropy. But the biggest contributors of all are black holes. In the early 1970s, a physicist named Jacob Bekenstein suggested that black holes, those regions where gravity is so strong that not even light can escape, must carry entropy. He argued that when something falls into a black hole, the information about its exact state seems to be lost to the outside world. And if entropy is a measure of missing information, that implies a huge increase in entropy. Bekenstein proposed that a black hole's entropy is proportional to the area of its event horizon, the spherical surface, beyond which nothing can return. At first, this idea sounded speculative, even absurd, because if black holes have entropy, they should also have a temperature and emit some kind of radiation, which contradicts the classical idea of a black hole being completely black and unchanging. Then, in 1974, Stephen Hawking's groundbreaking calculations showed that black holes aren't completely black. They can emit a faint thermal radiation due to quantum effects near the event horizon. This Hawking radiation implied that black holes do have a temperature and therefore entropy. And not just a little entropy, an enormous amount. Even a relatively small black hole contains more entropy than anything else of comparable size. For example, the supermassive black hole at the center of our Milky Way galaxy, about 4 million times the mass of our Sun, has on the order of 10 to the power of 91 units of entropy, a 1 with 91 zeros after it. That is roughly 1,000 times the entropy that the entire observable universe had just after the Big Bang. And that's just one object. When you tally up all the black holes that are thought to exist in the universe, the giant ones in galactic centers and the countless smaller ones formed from collapsing stars, their combined entropy utterly dominates the cosmic entropy budget. Current estimates put the total entropy of the observable universe at about 10 to the power of 104 in Boltzmann units, and almost all of that is in black holes. By contrast, the entropy in all the stars, gas, and cosmic photons is relatively negligible. To put it another way, the entropy of the early universe was essentially zero compared to what it is now. It was only a tiny fraction of a percent of the current entropy. Why the universe started out in such an extraordinarily low entropy state remains an open question. The British physicist Roger Penrose has emphasized how special that initial state must have been. He estimated the probability of a random universe beginning with entropy as low as ours to be outrageously small, a number so absurdly large it defies comprehension. One proposed explanation comes from the theory of cosmic inflation, which suggests that a tiny fraction of a second after the Big Bang, the universe underwent a burst of rapid expansion that smoothed out any irregularities and left it extremely uniform, hence very low entropy from gravity's perspective. Another viewpoint is the anthropic principle. Only a universe that began with a low entropy could evolve the complex structures necessary for observers like us to exist. So it makes sense that we find ourselves in such a universe, because in a high-entropy universe, there would be no galaxies, stars, or life to notice anything. In any case, the assumption of a low-entropy beginning, sometimes called the past hypothesis, underpins our understanding of the arrow of time. The direction from past to future is essentially the direction from low entropy to high entropy. Hawking's discovery that black holes radiate, while confirming that the second law applies universally, also posed new puzzles. If black holes slowly evaporate by radiating energy, what happens to all the information about the objects that fell into them? Does it disappear forever? This is the famous black hole information paradox. According to quantum physics, information about a system's initial state should never be irretrievably lost. Yet, if a black hole completely vanishes, it seems everything it swallowed would be lost from the universe. Many scientists suspect that a fully developed theory of quantum gravity, which we don't yet have, will resolve this paradox in a way that preserves information. Perhaps the information is encoded in subtle correlations in the Hawking radiation, or perhaps black holes never quite destroy information at all. It remains an area of active research. What we do know is that the second law of thermodynamics holds. Whether or not the information is somehow recovered, the total entropy accounting for the black hole and its radiation never decreases through the process. This staggering growth of entropy over time, from a smooth, low entropy origin to a clumpy, high entropy present, is the reason the cosmos has unfolded in the way it has. Because the universe started in an extraordinarily ordered state, there has been a vast entropy gap for nature to fill. All the structure and complexity we see around us are byproducts of the universe inexorably moving to fill that gap. The formation of structure, from galaxies to DNA, goes hand in hand with the overall increase of entropy. We never observe, for instance, a galaxy suddenly dissipating back into a homogeneous gas, or shattered planets reassembling into a pristine planet, because those would entail a decrease in entropy. The arrow of time, on the grandest scale, points from the smooth, low-entropy early universe to the clumpy, high-entropy universe we inhabit now, and it will continue to point that way as entropy climbs further. What lies at the end of this road? If nothing dramatic intervenes, the universe will approach a state often called heat death. In this final era, all energy will be as uniformly spread out as possible. Trillions upon trillions of years from now, long after the last stars have burned out, galaxies will be dark and quiet. Black holes will dominate for a while, slowly evaporating via Hawking radiation over unimaginable timescales. A black hole with a mass similar to that of our Sun would take an almost inconceivably long time to evaporate completely, far longer than the current age of the universe. The more massive the black hole, the longer the process. Eventually, after an incredibly vast stretch of time, the last black hole in the universe will dissipate. What remains will be a thin, cold soup of particles and faint, low-energy photons, so evenly spread out that nothing of significance will happen anywhere. This is maximum entropy, the cosmos in full thermal equilibrium, where no useful energy differences exist to drive any process. Time, at that point, would lose its meaning, because if nothing changes from moment to moment, one could not distinguish past from future. The arrow of time would have vanished. The universe will end not with a bang, but with a whimper, the faint hiss of the final heat dissipating. It might sound like entropy is the ultimate villain of our story, dooming the universe to an eternity of boredom and decay. But consider this. Both the extremely low entropy beginning and the extremely high entropy end of the universe are, in a sense, boring states. One is an almost featureless hot soup, the other a near featureless cold soup. It's the journey between those extremes that has been so interesting. Just as a cup of coffee and milk is most interesting while they're mixing, not when they're completely separate and not when they're completely blended into uniform beige, the universe is most interesting in this middle era where entropy is between the extremes. In this middle, gradients exist and complex structures can form. Stars, galaxies, planets, and life are like the intricate swirls in the coffee as the milk mixes in, transient eddies of order that arise along the way to equilibrium. Eventually, they'll dissipate, but for now, they add richness and beauty to the cosmos. We live in that creative mid-time. The universe is around 13.8 billion years old, but it's still far from heat death. Our sun will shine for another 5 billion years or so, and even after it's gone, new stars will continue to form for trillions of years in other galaxies. In this era, thanks to the low entropy initial state of the cosmos, we have energy flowing from hot to cold, from stars to space, and we get to surf on those energy flows. Life on Earth, for example, takes advantage of the sun's heat and the cold of space to fuel the processes of biology. Even Earth's climate and weather are manifestations of entropy in action. Sunlight heats our planet unevenly, mostly at the equator, and that concentrated heat then disperses toward the cooler poles and into space, driving winds and ocean currents in the process. Sometimes, the energy organizes into highly structured phenomena like hurricanes or thunderstorms. A hurricane, for instance, may appear as a beautifully structured, almost living system, but it's fundamentally a huge engine moving heat from warm tropical oceans to the upper atmosphere, leaving behind a trail of higher entropy. The ocean cools, the air heats, and everything becomes a bit more mixed. In general, all weather, wind, rain, storms, can be seen as nature's way of redistributing energy and smoothing out temperature differences, in other words, increasing entropy. We humans and other living creatures, in turn, depend on those flows and gradients. In a very real sense, we live off the universe's low entropy, the sun's ordered energy and the cool darkness of space, which keeps Earth far from equilibrium and allows complex, interesting structures to persist. By understanding entropy, we gain a profound perspective on why things happen the way they do. It ties together phenomena from the everyday to the cosmic. Why does a hot object cool down? Entropy. Why do we age, and why is it impossible to unbreak a broken glass? Entropy. Why does the night sky shine with stars now, when in the distant future it will be black and empty? Entropy. The concept often gets reduced to disorder, but as we've seen, it's more nuanced. It's about energy dispersing and systems moving toward the most probable state. It tells us that certain processes are irreversible because they lead to states that are astronomically more likely than the states we started with. It explains why we remember the past, but not the future, and why causes always precede effects. We have records and memories of the past because creating a physical record, whether writing in a journal or storing a memory in our brain, is an irreversible process that increases entropy, embedding that information in the world. We cannot have memories of the future because those physical records haven't been created yet, and to pre-record a future event would require undoing and redoing entropy later, which doesn't happen. Similarly, cause and effect obey the arrow of entropy. A cause occurs, say a vase is knocked off a table. Entropy increases, the vase shatters and glass pieces scatter, and then we see the effect, a mess of shards on the floor. If entropy could decrease spontaneously, we might witness bizarre inversions of cause and effect, shattered glass pieces flying up to reform a vase before it uncauses itself off the table. But in reality, such things never occur. The thermodynamic arrow underlies the psychological arrow of time and the causal arrow. All arrows of time we experience align with increasing entropy. Far from being just an abstract scientific idea, entropy is a central character in the story of the universe. It is the reason there is an arrow of time and a direction to history. It's why living things need to eat and stars need to burn their fuel. It can be destructive, causing ice to melt, metal to rust, living creatures to age and eventually die. Yet it was also instrumental in creating the stars and planets and the conditions that allow life to exist in the first place. For we humans, all these grand ideas have personal implications. Our bodies, for example, generate entropy, as we convert food into energy and motion, which is why we radiate body heat and eventually wear down with age. Our own internal order slowly breaks down over time. Every machine and appliance around us, from a smartphone to a car engine, must obey the second law, constantly expelling waste heat because of entropy. Even our thinking process has an entropy cost. Forming and erasing memories in our brain is accompanied by tiny increases in entropy as neurons fire and chemical bonds break and form. In a philosophical sense, entropy reminds us that change is inevitable and that nothing stays ordered forever. We see this in our own lives as aging and decay. But rather than viewing this as purely negative, we can find inspiration in it. The fleeting order we create, in our lives, in our technology, in our art, exists against a grand backdrop of ever-increasing entropy, and that contrast gives it meaning. We build structures, make memories, and strive for knowledge, knowing that one day they may fade, but that impermanence is part of the beauty of the universe's evolution. Often called the most misunderstood concept in physics, entropy is actually one of the most enlightening. It reveals the one-way choreography of nature, from order to disorder, and yet shows that this march toward disorder produces wonderful complexity along the way. Yes, the universe will eventually wind down, but not before it has produced galaxies, stars, planets, oceans, trees, and minds capable of contemplating it all. In the story of the universe, entropy is both a destroyer and a creator. It dissolves order, but in doing so, it paints the tapestry of our existence. By grasping this concept, we can better appreciate the delicate balance between order and chaos that shapes everything around us, and understand our place in this magnificent, irreversible journey through time. In every direction of inquiry, from physics and chemistry to biology and cosmology, we encounter entropy's fingerprints guiding how things evolve. Our knowledge of this concept not only lets us predict and harness natural processes, but also deepens our appreciation of the one-way journey that is time's arrow.